there are important parameters which you want to extract when you want to analyze the NMR spectrum of molecules. Right? So, what are the parameters which we will see? And these parameters are essential for characterizing the nature of the molecule or the phenomena that are happening inside the system, whether there is dynamism inside it, what kind of dynamism is present. To analyze all of these factors, so you must be able to extract these parameters from the spectrum. Okay. So what are these parameters? So let's quickly define these parameters. The first of those is called the chemical shift. Chemical shift incidentally was discovered by Dr. Liu several years ago in 1950, and in the high resolution case it was actually discovered by Professor S.S. Dharmati, who actually started the NMR group here in TIFR. So he was actually doing a postdoc with Felix Bloch in Stanford. And at that time, their aim was to measure the magnetic moments of nuclei. They didn't know about chemical shifts, of course, before that. So they only knew that the nuclei have magnetic moment, and you want to measure the magnetic moment to calculate the magnetogyric ratio as another property of nuclei, because the emphasis was on nuclear structure, how to characterize the nuclear structures, understand nuclear structures, and things like that. So he asked Dharmati to record an NMR spectrum, and he put the sample of alcohol. Typically, you will put the sample of water or something, which is plenty. And he put the sample of alcohol for no reason. God knows what reason he used that sample. And he got 3 lines in that one. And you will see that we have very poor resolution, of course. We got 3 lines. And he went and showed Doc, see, I got the 3 lines. He said, what? How can you get 3 lines? All the proton spectra, these are all protons. Magnetic moment of proton is all the same. So how are you getting 3 lines? There must be some impurities. This is wrong. This is not pure sample. So go and do it again. So he did it again. Again he got the 3 lines. He still didn't believe it. So, but nevertheless they published the paper without Felix Bloch. He didn't accept. So Arnold, Packard and Dharmati, that's the paper. So, and then it turned out that, okay, finally, what they are doing is right, and this is a new phenomenon that they have discovered. And this happens because of nuclei are not bare nuclei in your molecule. The molecule consists of other things inside, and that is electrons. So you have electronic cloud in a molecule, and therefore the electronic cloud sort of screens the nucleus. So if I have a nucleus here, then it has all the electronic cloud around it. Depending upon what kind of a structure which is around it. And once you introduce a magnetic field, it induces currents in this electronic cloud, which tends to produce a field which is opposing by and large the externally applied magnetic field. And therefore, you see the nucleus sees a field which is different from what is externally applied, and that is called as the screen. Okay, the nucleus at the site of so if H0 is your DC field, the field at the site of the nucleus, if I call it as H local or HI for nucleus I, this is given by H0 into 1 minus sigma I. And this is sigma I is called the screening constants. Okay. So the change in the field, if you see, it is not only proportional to the n sigma I, but also is proportional to the H0 itself. So the field which is seen is H0 minus sigma I H0. Therefore, it is proportional to H0 as well. However, what is important for us is the sigma I. Sigma I is characteristic of the electronic cloud. So if you want to characterize the electronic cloud, I must remove the H0 dependence. Okay. Therefore, I want to normalize the these deviations with respect to the H0 field. Therefore, I divide this by H0 and then I get a number which is different from this one. So some kind of a normalization is done, and typically we take a reference. HR is the field at a reference nucleus and then we define an entity called delta I is equal to HR minus HI divided by HR into 10 to the power 6. HR is a reference nucleus. You can choose anything. Various kinds of references are used for different purposes, for protons, carbons, nitrogen, whatever. Different kinds of references used. And with respect to that reference, you see how much is the deviation for this, and divide it by HR of reference. And why do you multiply by 10 to the power 6? Megahertz. So you want to get a good number. I don't want to get a number which is like 0.0005001 or 2 or things like that. So I want to get a number which is reasonably good to remember. So and this is called as the chemical shift. Now if you want to further simplify it in terms of frequencies, I can write the same thing. Instead of the field, I will write in terms of the frequencies. Now I will write mu I minus mu R divided by, I make another simplification here. Instead of mu R, I will write mu 0. Because the deviation is extremely small. For any nucleus, if you take, the deviation is extremely small. Therefore, compared to that, if we ignore that deviation, put in the main magnetic field, the mu 0 frequency itself, it's not going to affect your number here, deviation very much. The normalization is not going to affect you so much. Therefore, you use this as the spectrometer frequency itself. If I say 500 megahertz, what does it mean? It has to do with respect to the proton absorption frequency. That's the given magnetic field, bare nucleus. So I put the spectrometer frequency here as mu 0. Instead of mu R, I put mu 0 here.
So this is when
Mu 0? So it is a spectrometer frequency. The spectrometer frequency, mu R is the absorption frequency of a particular nucleus. Okay. And if I have a spectrometer frequency of 500 megahertz, let's take 100 megahertz, and how much will be the spectrometer frequency, I mean the mu R compared to that? So if I have mu 0 is equal to 100 megahertz, okay, and if mu R of some reference compound or reference nucleus, it is, let's say, 99.99995 megahertz. Because I was making some deviation from it. How much difference is going to make here if I put in mu R or mu 0? This difference is in hertz. This difference is in hertz or kilohertz. Okay, a few kilohertz, or even sometimes even in hertz. So if it is 100 or 200 hertz here, and if I make this the division by mu 0, which is either I put 100 megahertz or 99.9995 megahertz, it's not going to make a difference, right? So therefore, I am justified in putting this number as mu 0. Okay, it simplifies the calculation. Otherwise, every time you have to find what is the reference frequency, nucleus frequency, and then go and find out what is the frequency and then calculate. So it is much more unnecessary complication. So therefore, now you see this is a dimensionless quantity, right? Chemical shift is now a dimensionless quantity. This is in hertz, this is also in hertz, therefore it has no units, it is a number. Okay? So if I record a spectrum on 100 megahertz spectrometer or 500 megahertz spectrometer, this number will be the same for a given type of nucleus. If I am looking at the NH protons or CH3 protons in your molecule, regardless of what spectrometer frequency you will record it, it will be the same number. So we call this as, okay, this is 10 to the power 6 is also presented. Right? So this is, its units are parts per million.
And sir, why is it 3 y minus v1 not v1?
Oh, it is the frequency is minus of gamma of the PD.
Then denominator is also there, no?
That is a number. That is a normalization number. You can choose a sign. Earlier they used to write it as tau scale or the new scale. It doesn't matter. Whichever number is larger, you put that one. So you have mu is minus gamma h. Therefore you remove that. Take this difference to avoid that. Instead of that, you can put that minus, that mu I comes first. That comes positive. This becomes a negative over there. And here I am putting mu 0, so it doesn't matter. I am putting a number there. That is a normalization.
So mu 0 comes from H0, right?
Yeah,
So that if you convert that into mu 0, that will also give a negative sign.
Yeah, now here we are looking at the magnitude of the shift. How much it is? Okay. So you interpret relative magnitude. The relative changes between them, you interpret it as what is the extent of screening. Okay. And therefore this number is characteristic of the screening. Characteristic of the screening constant. Okay, depends on therefore on the nature of the nucleus. Now once you have defined a particular entity, okay, define a particular entity, then keep that definition. Keep that definition and compare. Now if you want to use the minus sign here, you can keep that minus sign, I don't care. But you use the same for comparisons afterwards. Okay. Keeping that, you should see which one is more negative or less negative, or which is more positive and less positive. That is what you want to use. And there are various kinds of reference nuclei which are used. So typically you use reference compounds. If you are looking at a spectrum of alcohol or something, you always put some other reference compound. How do you choose the reference compound? The reference compound is chosen on the basis that it must be quite robust. First of all, it should be stable, and it should be less sensitive to fluctuations in the environment, like the temperature, field denominator, of course, will broaden the lines. Other external conditions, it will be less sensitive, and it should be soluble in your solvent. Depending on which solvent you use, of course, you will have different kinds of references, and those ones are used. For proton, the common reference is TMS. This is tetramethylsilane. Okay, this is like silicon, and then of course you have 4 CH3 groups, and this is very symmetric. Therefore, it produces only one line. Okay, and that is and this one is obviously, it should appear at what? 0.0 ppm. Right? When there is a reference, that is 0 ppm. And everything else will be downfield. And if you are using, this is for non-polar solvents. For polar solvents like water, you use, typically there are two compounds, tetramethyl silyl propionate, also called as PSP. This also is of course 0 ppm, or sometimes you also use sodium 4,4,9-methyl, 4-silapentane, sulfonate. It is called TSS. There is,
Why you are taking these two TSP?
this is soluble in water. These both are soluble in water. But actually, this also gives a very strong signal for the methyl groups. This gives you only one signal. There is nothing, no other signal. However, this fellow gives more signals. This BSS gives more, it gives you the methyl signal, all right, at the same place as, nearly the same place as this one. It also uses some other signals. So often this can be a nuisance. Although you normalize, you take 0 ppm as a methyl group signal, but the other signals which are present here are a nuisance. Sometimes if you want to avoid, you can avoid that. But this one has some pH dependencies. So often you'll have to make a choice between one or the other, and once you choose one, stick to it. Okay, you can also use other references, and they will be attributed. Each one has certain chemicals with respect to each other. And for this is a proton. For nitrogen 15, you use ammonium chloride. Or you can also use ammonia itself. And for phosphorus 31, these are, I'm listing a few because these are ones which you commonly use. And incidentally, for carbon also you use that one, tetramethylsilane. You use that for carbon as well. TMS, you use it for carbon also. Here you use 85% phosphoric acid. Both proton and carbon 13 you can use. Now, so what are the factors which influence the chemical shifts? Individually, as I said, depends on the electronic screening, and therefore obviously nature of the structure of the molecule influences the screening. So what are the factors which influence the chemical shifts? First, electronegativities. Of substituents. For example, CH3Cl. So it depends, you compare that with CH4. Of course, CH4 is a gas, I'm just saying. So if there is something which is a liquid, so this is also a gas. So take some liquids, okay, where you have, let's take some other example. Okay, this is the liquid. Now, depending upon your CH2 or CH2, the Cl here, the chemical shifts will be different. Okay? Because this fellow has electron withdrawing nature, it changes the electron density around the proton, and that effect is different here compared to here, and therefore all these small protons become, they absorb energy at different frequencies, and then they are called as chemically different. And if you have the OH group here, of course chemical shifts will be different again, depending on what kind of electronegative substituent you have, different chemical shifts. And second, direct electrostatic effects. Electric fields, and then it will affect the magnetic field at the site of the nucleus. They produce electric fields, and then therefore they polarize the electron distribution. These electric fields produced by the charges, if you have a charge here, a charge Qi, and you have a nucleus here, mu I, and this electronic cloud around it, and this charge will produce an electric field here. Okay, so this electric field will therefore polarize the electronic cloud in this place, and that influences the chemical shift. There is actually a formula here. If I have a charge distribution, delta sigma is equal to 12.5 into 10 to the power minus 6 summation I to I cosine phi I divided by R square minus 11.0 into 10 to the power minus 6 summation 2I divided by Ri square whole square. This is the calculation. If you have a charge distribution around, there are a lot of positive charges, negative charges around somewhere, around this nucleus. And this is the angle between the vector connecting the charge and your nucleus with respect to the magnetic field.
That is 11.0.
Yeah? Huh?
That is 11.0.
11.0. Yeah. Okay. Here we see Ri is the distance between charge Qi and proton in the, this is for a CH bond, right? In the CH bond. And phi I is the CH Qi angle.
Summation the summation sign should be
Summation
outside
sign should be, yeah, you are right. Summation sign should be outside there. Yeah.
There is a nucleus, so the charges around the nucleus produce the electric field that will polarize the nucleus.
It polarizes the nucleus, no, not the nucleus. It will polarize the electronic environment around it. These are multiple charges around it. present somewhere in your system. Okay, they will all produce electric fields, and these electric fields will polarize the electrons around your nucleus. Therefore, the dipolarization changes the current in those electronic cloud because the electron distribution is changed. Therefore, the current induced magnetic field by those ones will be different, and that is how it influences the chemical shape. And then similarly for a dipole, if I have a dipole, delta sigma, this is for the dipole. Is equal to minus k with some constant times mu minus theta z into 10 to the power minus 12. K is a constant. And Ez is component of the electric field due to the dipole along the CH vector. Yeah.
What is that to phi?
Sorry?
What is that to phi?
Phi line. There's the angle. There is a bond angle.
Which angle?
No, I wrote that. No? Oh, I wrote it.
QI and
CH2I. Here I have written is the distance. Okay, I have written here phi I is CH2I. This is this bond angle.
Where H is the at which angle? At the point where H is.
Yeah. Suppose I have C, H, and my Q is here. Okay.
So where is EZ in this equation?
Z is, oh, this one. What was theta Z? Theta Z. When the characters are small, E and theta are not really the same to me. Okay, and we also have third is the, okay, let me go here now, because if I rub then sometimes we will have, okay, let me write the third, inductive effect. Organic chemistry should know this, right? What is an inductive effect? Polarizes the electron, pulls out the electrons, and therefore each group has certain inductive effect on the electron density. And that causes the electron density change. Then you will have hybridization. Hybridization also changes the electron density, whether you have sp3 hybridized, sp2 hybridized, sp hybridized, you will have different kinds of electron density distribution. And so we will not go into all those discussion there.
Sir, this inductive effect comes under the electronegativity of substitution, which you mentioned.
Electronic?
Electronegativity of substitution.
Electronegativity.
This is the first factor.
Yeah, you can. Yeah. And then you will have van der Waals van der Waals interactions. Then some of these are then have long range effects. Among these, on the long range effects, there is one particular thing which we would like to mention, and that is called the ring current effect. The ring current influences the electron density very clearly, and that also leads to what is called as anisotropy. What is the ring current effect? How does it change? Typically, aromatic systems will have that.
Sir, what are these long range effects?
Yeah, this is what I mean. One of the effects is the ring current effect. Okay, so you have electronic cloud here, electronic cloud there, down below, and the current moves here, right? The current in that electronic cloud circulates like this. Hello? Yeah? No, I'm busy just now. So this produces, the current produces current here, right? The current is going like this, it produces a magnetic field, and this magnetic field will flow like this. Okay? Now, this is the direction of the field. Your main field is here, let's say, H0. Main field is in this manner. This is one case where you can have an increase in the magnetic field at the side of the nucleus and now decrease. That's the reason I'm just picking up this example. So this is H0 field which is going like that. Suppose you have a proton or some other nucleus is being influenced by this magnetic field. Now it depends where that proton is. If you have a proton which is here, of course the field is going in this direction, it opposes this field. If you have a proton here somewhere, then the field direction is the same as this direction. Yes.
So you are considering the ring current to be in some
Pi electron.
Yeah.
Pi electron drop.
But it can be in the opposite direction as well.
Yeah, it can be.
Then for a single proton, that single proton explains two different types of field.
Different. I mean, of course, it will have different directions. Suppose the orientation is different. It's orientation dependent. I'm just giving an example. If the field is going like this, okay. If the field is going the other way around, if it's going in this manner, okay, then it will be coming down like that. And it will be positive here. Correct? So I'm just explaining how the field can influence your chemical shift. Okay. So if it is in this situation, if the proton is here, then it will see a reduction in the field. Here it will see an increase in the reduction in the increase in the field, and therefore it can cause a de-shielding. Okay. So when I say delta E is higher, the electron density is smaller. So chemical shift, what are the ranges of chemicals, that also we will see. So because of this, you can have a wide range of chemical shifts for different nuclei depending upon the structure of the molecule. Now in this case, we said the molecule is oriented in this manner, but suppose you consider a molecule which is oriented orthogonal, 90 degrees to this. Here it is, I put it parallel in this XY plane. But suppose it is oriented, the ring is oriented in this manner. Then the current will go in a different way, the field directions also will be very different. Therefore, it will produce different kinds of fields at the site of the nucleus, and it can influence your chemical shift. So here, the orientation of your molecule also becomes important. And that's what leads to what is called as anisotropy. Ring current is quite an important factor in anisotropic shifts. there are actually elaborate calculations on how much is the shift in this chemical shift. I will show you the figure next time on that one. How the change, there are plots with regard to the coordinate, depending upon the location of this proton around the ring current, around the ring, what are the chemical shifts, how we can calculate it. So those kinds of curves are there, ring current shift curves are there.
Sir, but in solution, all kinds of orientation of this molecule are possible if you are not considering confined environment.
Yes.
So,
Yeah. So you will see an average. You will see an
that
average.
time scale is comparable to your element time scale to get an average.
You will get an average. You will get an average.
So to
Yeah. But certainly there are certain orientations which are dependent on the molecular motion.
certain orientation only given differentiate.
Yes. If the motions are not that rapid as to average the entire chemical, then of course you will see a distribution. It also contributes to the relaxation, it also contributes to the line weights and all of those. But it certainly influences the average chemical shift. Average chemical shift will be dependent on what fraction of the time the molecule, the proton is in the direction parallel to the field or it is orthogonal to the field. With respect to that, it will depend upon motion of the molecule and the size and the nucleus which you are looking at. There is a relative motion between the two. Okay.
But you should get an average.
No, you will get an average. You will always get an average. But the average will also have a population distribution. Correct? The population distribution can vary depending upon which population has what kind of orientation.
So then this will be random from experiment to experiment.
Yes, you cannot have.
Even
No, it is a system.
first experiment and the in second experiment.
No. System. This is your solution.
Huh.
The solution is the same always. In your solution, the molecule is in a solution. That's always the same. That system is not changing.
If I do experiment 5 times on it, then
It will be the
five
same.
result.
No. Your molecular motions are averaging. Correct? It will average the same manner whether you measure now or later. It will be the same average. The population distribution inside your magnet, okay, once you put it in the magnet, that is going to be the same.
The average value will be same, but the
Yeah.
weightage for the different population under the
That will be
different for experiment to experiment, right?
No. Why should that be? It depends on the molecular tumbling. Depends on the molecular tumbling and it is characterized by the molecular properties. Molecular properties, they are dependent on the viscosity, solution properties. It will depend upon only those. It should not depend upon your magnetic field.
So here you are considering the ring current to be in the anti-clockwise direction.
Well, I just took an example in that manner.
Yes.
You could do that in the other direction. Therefore, there are, as I said, there are curves calculated for the ring currents depending upon where your proton is and how much is the shift going to be. Okay? And then you average over all these ensembles, then you will see an average chemical shift. If there is a rigid lattice, for example, then those calculations will tell you, okay, if it is here, it will be this much with the chemical shift, if it is here, this much will be the chemical shift, and so on and so forth. Okay? But if it is tumbling, and it will be an average of this. Now, why will the populations be different for the two cases? If their energies are different, if the two orientations are different energies, then they will have different populations. Okay? So, because then it will be distributed by the Boltzmann distribution. So according to the populations will be different. Then you will have the average of all of those ones.
Even if the molecule is rotating, if some proton is at the axis of this circle, and if something is outside of the circle in the addition, so if the molecule rotates, then the relative position remains the same. And the average quantity will differ just because of the position of the proton.
With respect to the field,
Yeah, it is there, but anyway, you rotate the molecule, which proton that was at the axis of the circle, it will remain there because the whole molecule is rotating.
yeah.
So average of that protons, set of protons, and average of that set of protons will be different.
Yeah, so if average of this proton will be the same.
This proton will be
Yeah.
the next set of protons.
But this one is different direction.
But you get a single chemical shift for, let's say, benzene.
You get a single chemical shift for this, you get a single chemical shift for this as well.
From this one. So then, if we calculate the field experienced in the previous equation you just wrote.
No, this equation, that equation is not for this. That is individual charges separated elsewhere. Monomoles.
Not that one, the previous one. That is delta equals to HR minus HI upon HR. So if we calculate the field that the proton is experiencing, we just get an average field, or we just get the exact field. I mean, when the proton, let's say the molecule, when the ring current is in the clockwise direction,
Yeah. So that is where anisotropy comes in. That's why this introduces anisotropy. Here the orientation of the molecule with respect to the magnetic field comes into the picture. If it is an isotropic situation, there it doesn't matter. Orientation doesn't matter at all. Here the orientation matters because of the anisotropy. Depending upon the orientation of the molecule or the molecular vector which we are looking at, with respect to the field, and therefore the anisotropy comes in. The anisotropy also contributes to the chemical shift. Anisotropy is an important factor which also changes the absorption frequency, right? Therefore, it also contributes to the relaxation mechanism because of this. Chemical shift anisotropy is also a contributor to the relaxation mechanism.
But in solution, you do not have any control over this.
No, you have no control. You have no control. And it is only dependent on your solution properties. What is your viscosity of the sample? What is the temperature? How fast the motions are happening? It depends only on those.
So how do you optimize to get reliable signal in case of such compounds?
I mean, there is nothing you can optimize. You have to see where you can get sharp signals. You want to get sharp signal. But sometimes you want to get the chemical shift anisotropy itself. You want to measure the chemical shift anisotropy, in which case, of course, you want to have as much anisotropy as possible. But if you are only interested in averaging out much more, want to get only one single sharp, then of course, you should increase the molecular motions. And the molecular motions are increased, you increase the temperature or reduce the viscosity, and such kind of things you can do. Okay. And there is another effect which happens, this is due to the paramagnetic effects, presence of paramagnetic paramagnetic shifts. And this happens if there are unpaired electrons around in your molecule. Okay, these unpaired electrons, they actually produce huge magnetic fields. Okay, and therefore typically the shifts caused by these unpaired electrons is very large. Sometimes it can go to several kilohertz. That sort of range they can cause, because this is caused by the electrons. The electron magnetic moment is much larger, right? And therefore, because of that, the field produced by the electrons is also very large. This can be a dominating factor whenever that is present. And then I have one last key, that is the hydrogen bond. Hydrogen bond, typically like for example NHO. Okay? So the NHO, we are looking at the chemical shift of the NH proton, the proton NH, and if it is involved in a hydrogen bond with oxygen, what it does, it pulls out the electrons, and therefore it changes the electron density around the proton, and this causes a shift downfield. Typically, if the electron density is lower, you will find the signal at higher ppm value. Delta ppm will be larger. That's called as the D shading. Larger value of delta means de-shielding, lower value of delta means shielding. Okay? So if there is a reduction in the electron density, then you have a de-shielding effect and you will have ppms occurring at larger values. Okay? Now typically what are the ranges? Now let's look at the range. With all of these, what are the ranges of chemical shifts? Ranges of delta. This for proton, this goes from typically this goes from 0 to 10 ppm. So I am saying typically, okay. But if there are hydrogen bonds, then it can go all the way up to 15, 16 ppm. Okay. And in a DNA, for example, if somebody is looking at DNA, you always have hydrogen bonds there. Amino acids, or in protons in the beta sheets. Well, beta sheets they don't go that far, but in the DNA NH2 hydrogen bond, NH10 hydrogen bond which are present, that typically goes all the way up to 15, 16 ppm. And otherwise, in the normal cases, all normal standard molecules, single molecules, you have the range between 0 to 10 ppm. The lower values are for shielded nuclei like methyls, methylenes, and such groups. And higher values will be for things like NH groups, the OH groups, aromatic rings. Aromatic rings also will come down. So you have therefore a sort of a qualitative idea as to what are the ranges of chemical shift for what kind of structures. So these have been tabulated very well. So therefore this is a very useful structural information when you want to characterize a molecule of interest.